Okay, now let me look at the last paper in this article, and this is the pedestrian stride length estimation from IMU measurements and artificial neural network based algorithm. So you can see that it is very active area of research trying to get to stride length estimation. So I would say exciting 4 papers, read them thoroughly, understand them well, and then you would perhaps also be at exactly the point where the needle has stopped with respect to the state of art. So what do these papers do? This paper says, this paper puts forward a stride length estimation algorithm based on back propagation artificial neural network based system using a consumer grade inertial measurement unit, that is the same one that most phones have, right. So any time you talk about pedestrian dead reckoning, there are 4 phases. They look at step detection, step or stride length estimation, heading estimation and navigation results update. See, these are the 4 basic steps in any of your application that you are looking at in this localization without GPS topic. You may have to do these 4 steps when you work with IMUs. Step detection algorithms include zero crossing method, peak detection method and autocorrelation method. Stride length estimation is complex because there are variety of motion patterns during walking or running. Patterns include walking slowly, walking normally, walking rapidly, running, texting mode, walking mode and all that which we already spoke about. Now this is also important, why your Weinberg expression is not so good. This is actually telling you why, and I discussed this already once with you. PDR is related not only to the number of steps but also the step length. This differs greatly among individuals and is related to the walking speed, we mentioned this already. It can vary, step length can vary nearly 40% among pedestrians walking at the same speed and up to 50% throughout the range of walking patterns of an individual. Within the individual itself there can be a variation, and 40% among pedestrians walking at the same speed, this is important. So getting to a very accurate K is no simple way, there is no simple way of getting to that K, which is just like a constant I mentioned, and that indeed is that's the struggle. People have spoken about the simplest approach of step length, take a constant model for one person, but that will not work because the model cannot adapt well whenever there is a change in pace. Linear relationship between step length and pedestrian height, some people tried that, but the variation of step length during walking was something that was not considered. Yang and Lee, another set of authors, identified close relationship between frequency and step length and proposed an algorithm to estimate the step length based on step frequency in some other work. The authors of paper 10 adapted this linear model for PDR. So a whole bunch of work on how to get to the step length are all referenced in this. Okay. The whole trouble appears that if you take this taking into account, you look at this sentence, taking into account step intervals, acceleration variance and inclination, the step length can be modeled by multivariate equation. Okay. A non-linear model with only one coefficient was proposed to estimate step length. However, this model's coefficient may vary between different pedestrians. So this is indeed the crux of the problem. So really one cannot go with all the existing methods, at least that is what this paper seemed to claim. And this paper also talks about how to collect data, because they have to get humongous amount of data before they actually conclude on anything about estimating stride length accurately. So they also, I suppose, connect the IMU on the foot because of its ability to give good signatures, but their data is collected from just 13 test subjects. That is the problem, it is still very weak because 13 is no number, it should be perhaps 130,000 to arrive at a very good conclusion, particularly if you are doing any neural network based systems where you do it iteratively, right. So, this is really the issue. Okay, so you can see that the toe is off, then you have heel strike, your toe is off, you have basically the same thing of heel strike and stride and stance. Heel strike and stance, these are the two things that they seem to be doing, and again you are back to the same expression, which is an empirical nonlinear model which is used for estimating the stride length. This is the famous Weinberg expression again back here. Of course, there is no n here, which is this is for a single step, I suppose, because there is no n, or n is equal to 1, you can say. This model seems simple because it has only one coefficient, and but in order to find the maximum and minimum vertical acceleration each stride, initial alignment must be completed, and that is where the whole difficulty is. And some people, and this paper goes on to substitute k as 0.55 and tries to come up with some expression, but miserably says that it is not the right way to do, because this is not going to work for several people. Then they propose this back propagation artificial neural network analysis to estimate the pedestrian stride length. So, what do they do here? As you know, any artificial neural network will have basically 3 layers. There will be an input layer, basic layers will be only, you should have a minimum of these 3 layers. You will have an input layer, you will have a hidden layer, and you will have an output layer. Something from the input is fed to this hidden layer, like a functional relationship there has to be a function, and from the hidden layer to the output layer you need a function, and from the output layer you need another function essentially. So, the output that you actually see will be in this expression nothing but the y hat or the y cap, which you will see out here, and then you will find an expression, you will find a function here. Essentially these are all non-linear functions, and we will look at these functions one by one. So, let us see this essentially you have inputs, which is just a set, what are the inputs that you feed, you will have to understand what are the inputs, and then what is this function here in the hidden layer, that we will have to know, and then we have to also know what is the output function, and also from the hidden layer to the output layer what is the function, that also we have to know. So, you need a function here and you need a function here, both places you will need a function. So, let us go and see what all these functions are all about. It can achieve, so what does neural network do? It can achieve non-linear mapping between inputs and outputs, consists of input, hidden and output, and its weights and thresholds are continuously adjusted to approximate the desired output, desired input and output mapping relationship. So, you need something and you need something, you have to feed something at the input, you must get a nice output which is where you will have a quantifiable relationship to the output. Now, the active function of the hidden layer is a sigmoid function. You could refer this reference 6, and in fact there are several such functions. One of the functions is indeed the sigmoid function that they choose, while the output layer is a linear function. Okay. So, this is a sigmoid function, the active function of the hidden layer is the sigmoid function, while the output layer is a linear function. So, this is x is essentially the independent variable as shown here. The input of neurons in the hidden layer can be described by this function here, this is the important function. So, let us understand this, this expression Vi is summation essentially of Wij xj I going from 1 to n naught plus some Bi. So, let us see what is this expression with respect to this picture. What you see here are all these green dots, you see how many 1, 2, 3, 4, 5, right, and then you see some hidden layers, you have see 4 other color blue color dots. Take this line here, this is a weight essentially, okay. So, and this is another weight, this is another weight. From this neuron itself you are mapping to other neurons in the hidden layer. So essentially it is one to many kind of mapping as you can see here, and essentially that is this Wij. So what is that? So let us see, Wij is the connection weight of the ith neuron of the input layer to the jth neuron of the hidden layer. So you can see, if you take this ith neuron of the input layer, jth neuron of the hidden layer, right. So essentially it is that weight that we are talking of here, fine. Now it is just not that, right. So it is into xj. Xj means what? There are 5 inputs here as well, there are 5 inputs here as well. So you may have to look at 1, 2, 3, 4, 5, you can see this is again another one here and another one here and so on. So you have inputs, right. So this xj essentially is nothing but it denotes the input of the jth neuron of the input layer. Now we will look at what is this xj shortly, but just look at the expression, understand the expression from this picture's perspective. N0 is the number of neurons in the input layer, and Bi is some bias, it is essentially a bias, is the threshold of the ith neuron of the hidden layer. You can leave that for the moment, keep it out for the moment. Now what are those inputs that you are going to feed is the most important part, okay. So let us look at them. What you feed, we take 5 variables, this is nicely marked here. 5 variables which may be closely related to the stride length are studied using data collected from 13 subjects aged 22 to 29. These variables are include mean stride frequency is f stride, maximum acceleration in the walking cycle ACC max, acceleration standard deviation sigma ACC, mean acceleration ACCM, and height of the test subjects h. These are the xj's which are coming in from that expression that you see, and essentially they are trying to train all the, take these as inputs, train this model recursively and then come up with some output y hat. You see y hat here, you see ultimately you get a y hat here. Now what is y hat? Y hat being the output is the output of the neuron network, N1 is the number of neurons in the hidden layer, Wi is the connection weight of the ith neuron in the hidden layer to the output layer. This is important in this because you are looking at a function output of the BPANN function, you have to look at the output layer, and the definition of xi is the same as that of 8. 8 is this expression which is given by the output of neurons in the hidden layer, can be formulated as a sigmoid function shown in the other paper which is given by this expression here. So essentially your y hat is the output of the neuron network, and these are the inputs that are being fed to the system. Then what they do, they run this neural network and then they sort of try to correlate the stride length as accurately as possible to ground truth, and they have some results appearing here. So this paper is also interesting because it applies back propagation neural network, artificial neural network, and this further what it also says is, in this part it says how do you calculate the inputs. You need f stride as we discussed. So you get f stride from the time interval of each walking cycle, and then you get to f stride and so on. So essentially this is also saying that you could apply these modern techniques in order to arrive at very accurately the stride length. So the conclusion of this work is 5 variables in the walking cycle were used as an input vector to the back propagation artificial neural network, and they claim that it is better in performing pedestrian stride length and it has a precision in the stride length estimation. So, let us look at the source code, just as a sort of a sneak preview into the source code of the IMU based localization scheme. I have put down 5 important steps here, and we will try to run through the source code based on these 5 steps. First, let us start with the extraction of sensor values using the Android API. Why I made this assumption is because I am assuming that each one of you have a mobile phone, smartphone with you, and therefore IMUs are integrated into such smartphones. So, let us see where exactly in the code you will find this extraction of sensor values using the Android API. What this actually means is you are telling the hardware that these are the sensors that I want to use, and you are informing, sort of you are using the API for the purposes of registration. Okay, so, it is essentially registering to the API that these are the sensors of interest, and this is what I am going to collect data from. So, let us look at the source code part which is specific to that this section. The one that is highlighted on the screen here essentially is the portion related to extraction of sensor values and that registration part. So, let us highlight again once again. Okay, so that is the extraction part. So, remove the highlight now. Alright. So, what it actually says is that you are talking about accelerometer. Can you point to the accelerometer? Yes. Then there is the gravity part which can come out from the for each one of the axis. So, that gravity part of the accelerometer data is also pulled out. Then you can get something from orientation, which is essentially coming from the magnetometer, and then we look at. So, accelerometer and magnetometer are the two main sensors that we are trying to use, because as you know magnetometer would be required every time there is a turn in a corridor, right. In a inside indoor corridor you are turning, you need magnetometer values. So, this is the first step. The second perhaps is the most critical part, as I mentioned, that sensor values coming from these IMUs are extremely noisy, and it is really, I would say, you have to spend sufficient amount of time trying to find out what is a good filter and sort of do a proper filter design of the value, so that you can denoise the sensors. So, essentially it is a filtering step. You see the code that is highlighted is essentially the part of the filtering here, and for in our code we used a Butterworth filter. The order of the filter, the cutoff frequency, type of filter, all this you will have to keep trying and arrive at something very good, so that you will be able to get noise free sensor data. That is the key goal, and therefore you will see that all the coefficients of the filter are all out there, and those are 3 ones which are highlighted clearly, and this is essentially the filter design part of the code. The next is, once you have nice filtered output coming from these sensors, you will have to basically run you will have to find out you have to do a step count. In order to do that, you essentially have to find out, you have to detect peaks essentially, right. Kindly recall the picture that we mentioned about the minimum and the maximum that we will have to locate, and therefore the step count essentially hinges on good detection of the minimum and the maximum part, which essentially gives you the step count. So, now you can see that this part of the code essentially is talking about the step count, the whole code which is essentially talking about the step count. Then comes the stride length estimation. As I mentioned to you, the Weinberg expression is a very common expression, and this Weinberg expression is actually highlighted here. You will see that the last point essentially is that 0.438, is actually that k value, right, which you will have to find through extensive measurements, characterization and so on. And the final thing is that whatever you do, it becomes specific to that person. So, the whole investigation in this area is actually to generalize and somehow obtain or automatically learn this value of k depending on who the phone is, in whose hand the phone is actually held, right. So, essentially that is about the stride length estimation. We mentioned, I already showed you one part of the code where the heading from the magnetometer is available, and that data you will use if you are essentially using it for detection of turns and so on. So, in a sense this is what you will have to get to put together when you try and prototype your application. Now, all of this what we have just seen now is for one mode essentially, right. It could be for texting, swinging and running. This specific code that I showed you on screen is actually for texting mode. You will have to now see how to improve this basic code for swinging as well as for running. And also please note that we will give you a bare bone code where the core algorithm will not be mentioned here because we have some IP issues. So, you will find in one place insert your code here, right. So, what you should insert will also be mentioned. So, at exactly that point you will have to write your own code and make a nice application for let us say texting mode. So, in a sense this is the code for trying to find if you want to do localization without IMU without GPS and using IMU sensors. Thank you.